This is section 4.3, and here we're really going to deal with the case that we did not deal with last time. In section 4.2, we dealt with the possibility that the auxiliary equation has multiple roots. That is where perhaps it just barely hits the x-axis or the r-axis in this instance. We've also dealt with the possibility that it has two roots, but now we're going to deal with the possibility that it has only complex roots. It wouldn't hit the r-axis at all. So you may recall that if the roots are not real, then the discriminant is less than 0, b squared minus 4ac. You're still going to get two solutions, though. They're just going to be complex solutions. So we're going to let R1 equal alpha plus I beta. Recall that I is what makes these complex. I is equal to the square root of -1. It is an imaginary number. R2 is alpha minus I beta. And alpha and beta are actually known. Alpha is negative b over 2a, and beta is the square root of 4ac minus b squared over 2a. Now, we want to use the methods from the last section to find solutions to these types of differential equations. But we run into the issue of needing to determine the value of e to the it, since I is the imaginary number, square root of -1. Recall from section 4.2, we were supposing that the solutions we were going to find were going to take the form y is equal to e to the rt. Well, if the r that we solve for now is going to have some I component to it, e to the alpha plus I beta times t, we're now dealing with e to some complex power, and we don't intuitively really even know what that means. So we're going to go back to the Maclaurin series. You may recall that the Maclaurin series for e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So we can just plug in it for x. So we get, everywhere there's an x here, we're just going to substitute it with it. So 1 plus it. Now note that everywhere that I is squared, I squared is just equal to -1. So let's just stop for a moment here and look at this. This should be it squared, but I squared is -1. So all that happened is that I squared became a -1 instead of a +1 as it was before. And so on. Now, what are we doing this for? Are we actually going to reach anything here? E to the it, here's what it equals. Let's separate it into its real components and its imaginary components. So we'll take everything that's multiplied by I, and we'll look at it on the right, and everything that's real, and we'll look at it on the left. So we get these two infinite series. I was about to call them smaller series, but they're infinite. But what you may recognize is that these are familiar series. These are actually the series for cos of t and sine of t. So e to the it is actually equal to cos of t plus I times sine of t. Now, can we make any use out of this? Let's look at the type of solution we would have had before. We were used to getting multiple solutions, and then we would make a linear combination out of them. Well, we're going to do the same thing here, but we're going to replace R1 and R2 with these complex solutions, alpha plus I beta and alpha minus I beta. Now, remember, when you have powers with these plus or minus signs in them, you can break them up as products. So e to the alpha t, that's fairly normal. That's not going to cause any problems with us because that's just e to the power of some product of real numbers. We can work with that. But e to the I beta t or e to the negative I beta t is a little new for us. What are we going to do with that? Well, we're going to use our equation that we just got, what e to the it is equal to. It's cos of t plus I sine of t. So We perform that substitution. Everywhere that we have e to the I beta t, we get this cos beta t plus I sine beta t business, and then the negative version over here. Now, something very slick and important is what happens from here to here. It's a simplification step that is going to deal with this negative b that is inside these brackets that we don't want. We know from our two old principles about sine and cos, sine of negative x is equal to negative of sine x. So I just brought that negative out front. And cos of negative x is just equal to cos x. So with cos, I was just able to eliminate the negative altogether. So that's how we reach this kind of final form. Now, when we're dealing with these differential equations, we're going to need to know what the derivative of this y is. And this gets a little bit messy, but we'll give it a shot. There is quite clearly going to be a product rule here, because when we're taking the derivative, we have our function e to the alpha t times some function in terms of t. Here, the same, e to the alpha t times some function in terms of t. So we take our two product rules, add them together, and this is our dy dt that we're left with. Remember that when you take the derivative of cos, for instance, it becomes negative sine, but this b factor is going to come out front by your use of the chain rule. So that's how we get all these b's coming out. Now, let's see if we can make use of this large derivative equation. We have an initial value problem. Y double prime minus 4y prime plus 5y is equal to 0. And we have our two initial values. Y of 0 equals 10 and y prime of 0 equals negative 1. As before, we're going to jump straight to the auxiliary equation. R squared minus 4r plus 5 equals 0. We plug it into our quadratic formula, and we get a negative under that square root. That's our sign that b squared minus 4ac was less than 0, and we are going to have some complex solutions. So our answers are 2 plus or minus I. So R1 is equal to 2 plus I, R2 is 2 minus I. So this gives us what y is equal to. Y is equal to C1 e to the 2 plus I times t plus C2 e to the 2 minus I times t. Now, we would normally be content with such a solution, but these i's, they still don't quite make sense to us. It's something complex in a power, so we need to simplify. And that's why we've been doing this sine and cos business. We actually know what e to the it is equal to now. Y is actually equal to this equation, where you plug in alpha equal 2 and beta equal 1 to the equation we solved for up top. Now, let's see what happens when we plug in our initial values we were given. When t is equal to 0, we have that y is equal to 10. And this simplifies just as in last section. We have C1 is equal to 10 minus C2. Important note. I times sine of 0. Well, sine of 0 is just 0. So every time you see that, that just disappears. Cos of 0 is just like e to the 0. It's equal to 1. So that's how this simplified as such. Now let's see what happens working with the derivative. See if we can get another such equation. Well, the derivative, again, it's a much larger thing here. We're going to plug in the initial values we were given. When t is equal to 0, dy dt is equal to negative 1. And again, it's going to simplify greatly. All these sine zeros disappear. All these cos zeros, they just become 1. All these e to the zeros, they just become 1. Our simplified form here for the derivative, though, still has i's in it, and that worries us slightly. We're going to plug in for C1 what it's equal to. It's equal to 10 minus C2. We're going to expand this. Simplify, 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 simplify. And we're going to get that C1 is equal to 10 plus 9i over 2. After getting that C2 is equal to 10 minus yi over 2. And we can plug that in for C1 and C2. But we didn't really solve our problem of having i's. There's still i's written all throughout this. Things didn't cancel out the way we were hoping. Normally, we'll stay away from decimals. Fractions will be just fine for this course, but to make it a little easier to read, I thought this would be a good instance to use the decimals. 10 plus 9i over 2 can just simplify as 5 plus 4.5i. So that's all we've done from this step to here. Now, again, we're trying to simplify anything we possibly can here. And we do actually find a couple things that are going to cancel out for us. This plus 5 plus 4.5i times I sine t is going to cancel out with this negative 5 plus 4.5i I sine t. So we've greatly reduced the number of the number of i's we're dealing with, but there's still one in there we just weren't able to get rid of. So this effort, it was all mathematically correct, but we just didn't succeed in what we were trying to do. So that's why we say, however, we can do better than this. According to Lemma 2, this is on page 167, both the real part and the imaginary part are themselves solutions. And the proof of that is on page 168, if you would like to read up. So y is equal to c1 e to the 2t, so on. This is from before. We're just going to simplify. And by simplify, I mean carry through these multiplications. So since the real part and the imaginary part are both solutions, we would like to find a way to quickly say what are the real and imaginary part. Well, this is our equation for y from way back before we even plugged in the initial value components. And we just want to multiply through, push the pieces around until we can factor out I on one side and call that the complex portion, the imaginary part that is, and call the other part the real part. So here we're just multiplying through by c1 e to the 2t, c2 e to the 2t, multiplying through term by term. And we're just going to move all the stuff that has to do with y to one side. So this is our imaginary part, and this is our real part. Now, we have c1 plus c2 and c1 minus c2. For simplification, let's just call these new variables. We'll call c1 plus c2 d1 and c1 minus c2 d2. And I just misspoke. I said they were variables. These are just constants. So y is now equal to d1 times e to the 2t times cos t plus d2 times e to the 2t times sine t. This is the real part. This is the imaginary part. Now we actually have y written in terms of only real numbers. So we're going to try to evaluate the initial value problem one more time. So let's plug in t equal to 0, y equal to 10. This time it simplifies very nicely as 10 is equal to d1. Now with the derivative, we will, of course, take a derivative of our new function using the product rule where necessary. And once we have it simplified to the best of our ability, we are going to plug in t is equal to 0, y is equal to -1, y prime is equal to -1, that is, from the question. And this is going to simplify to this point. -1 is equal to 2d1 plus d2. But we know what d1 is equal to. It's just equal to 10. So we can plug that in. So d2 is -21. So we now have our values for d1 and d2. And there are no imaginary numbers to be found. So this is the method we'll use when we have an auxiliary equation that does not touch the r-axis. So we only have imaginary solutions, complex solutions, that is, to still reach a real answer.